In this problem, what I want you to do first is to determine what's going to happen when you react 26.98 grams of aluminum with excess hydrochloric acid. So see how many grams of H2 you're going to form. Pause the video and give that a try. Okay, now it's nice in the setup here. You can see that I've given you 26.98 grams of aluminum to start with. Now our molar mass is going to be 26.98 grams of aluminum in 1 mole of aluminum. Like I said, I was being nice. Our grams have cross-canceled, and so have aluminum, and so now we are in moles of aluminum. Now we're going to convert from moles of aluminum into moles of hydrogen. So we have moles of Al on the bottom, moles of H2 on the top. I look up here and I see that I have 2 moles of aluminum per 3 moles of H2. That is an effective thing that I just did. If you leave these blank and you write in your units and your species, then you fill in your values, it's a really good way to keep from accidentally putting things in the wrong places and throwing things off by a major order. Okay, so I've got moles of aluminum cross-canceled. I'm in moles of hydrogen now. Now I need to determine how many grams of hydrogen I have. So I need to go from moles of H2 into grams of H2. For that, we're going to need the molar mass of hydrogen. We know that the atomic mass of hydrogen is going to be 1.008 grams per mole. For H2, it's going to be double that. If you don't have this number memorized, it's a sign that you need to do more problems. It's not something I'm going to test you on. In fact, it'll definitely be on the periodic table on your exam. But if you're doing enough problems, you've got that thing memorized by now. And if you're using other periodic tables, you might even know it all the way out to be 1.00794. Now, anyway, you're going to have 2.016. And you can see I've just multiplied that by 2, 1 for each of the 2 atoms of hydrogen. So we'll be in grams per mole. In other words, 2.016 grams in 1 mole. If you haven't picked up on this yet, the reason that you don't write grams per mole on the top is because you're saying you have this many grams in 1 mole. So when we have grams per mole, we spread it out like this. We just break it and turn it into the fraction. What we're saying is grams in 1 mole. I know some people sometimes get to about the halfway point of the semester and haven't realized that yet, so I just wanted to point that one out. We cross-cancel our moles and our H2. We are now in grams of H2. So we need to calculate how many grams of hydrogen we've formed. For that, we're going to need a calculator. Okay, now we do 26.98 divided by 26.98. I know, I could have just typed in the number 1. That's pretty intuitive, but I still wanted to show it. We're going to multiply by 3, divide by 2, times 2.016. We hit enter and we get the value 3.024. So 3.024. 3.024 what? And do we have sig figs? Well, I've got 4 sig figs for exact, and 4. So the 4 sig figs is correct. I am in grams of H2. So this is our waypoint answer. This is how many grams of hydrogen I think are going to form. Now what I want you to do is determine which one do you think that is? The theoretical yield, the actual yield, or the percent yield? Okay, that's going to be the theoretical yield. Because if everything goes exactly as we have planned, then that's the amount we should get. However, in the lab, things don't usually work that way. Notice what we're doing here is we're taking a chunk of aluminum, we're dropping it in some hydrochloric acid. That means we had to either have it pre-configured so that we had a little ledge inside of an airtight container, except for one little tube. There's got to be a little ledge where the aluminum can sit. So we can just suddenly tip it, have that aluminum drop in, and now every bubble that comes out is going to be hydrogen gas. And we're going to collect it somewhere else to weigh it. That's going to be a little bit tricky to pull off, right? There's probably going to be a leak somewhere in there. Or maybe we don't get the lid on quickly enough because we probably didn't have a specialized glass container with a little ledge on it for it. We probably don't have that kind of hardware, even in a research lab. So we're probably going to have a little bit lost. On top of that, maybe not all the hydrogen bubbled loose from the water that it was in. All these things mean that when we actually measure how much we got, we're probably going to find that we have less than we think we should. So that means what we think we should have is going to be theoretical yield. If I tell you that when you weighed it, you got 2.012 grams H2 actual. Well, how do we know that? Simply put, you wouldn't in a class unless we told you this is what you actually got. So the problem is going to tell you this was your actual yield. In the research lab setting or in the laboratory class setting, you'll measure actual yield as well. So what do you do to determine your percent yield? Well, you grab your calculator and you say your actual yield divided by what you should have had theoretically will tell you your percent yield. So we grab our calculator and we'd say 2.012 divided by 3.024 times 100 gives us 66.53%. So 66.53%. Now often we'll round that to be a whole number because if we're using percent, we almost always just like to use whole numbers for it. So it's probably going to be reported somewhere as 67%. This is the correct answer in terms of sig figs, but this is the common way that we would end up writing it. That's the distinction between your theoretical yield, your actual yield, and your percent yield.